questions below, and I'll respond quickly or in the next episode of Louis Yam.
Hey everyone, oh my gosh, class is over. Class is no longer over. Who's in the chat? Feel free to say hi. It is time for office hours this week. I feel like maybe it's still better. We gotta do like all this, like fixing the lights around here, fixing your sleeves around here, fix it all up. Okay, well it is time. Like the weather. Oh, I thought someone appeared in the chat. Weather made my hair a little flatter. I think it's time for a haircut. We gotta do it. And time for Monster Energy drink. It's time for a lot of things. So with that, let's get logged into Pearson here. I don't have Mubot to wait. What's Mubot doing? What are you doing, Mubot? Mubot waking up right there. Gotta log in and do some Chapter 7. Chapter 7, Assignment Manager, Chapter 7. Chapter 7 is a very good one. They changed the way this looks. When does Chapter 7 do? Chapter 7 homework. October 3rd. So we got some time. October 3rd is not until when? Thursday, Friday? Somewhere around there. Let's think. The 31st is Tuesday. So then, what was it? Is it due Friday? Ooh, people, when things are due Friday. Friday's not a good day. Have things due. Okay. Let's go over here and let's do the full assignment. Let's go put it in the notes, and then we'll say to people, hey, we've done the full assignment, check it out. Get 100 on the homework. Okay, so we got here at 3:03. We got Stant 201, Chapter 7, homework, question 1. Let's go do it. Okay, this is an interesting one. It's all about theory to start right here. And they use some interesting words. We're going to kind of go through the theory and explain what's going on. Some of the residuals here. Let's take a little screenshot and talk about these. So you should know what these words mean. That's the important part. Remember, we are going through the full assignment, but then we also want to understand the answers to this and why we're getting these answers. So when it says a residual, you have to know what a residual is. A residual is found by the formula E, which is what a residual is, equals the actual minus the predicted. So an actual point is a dot. That's what the actual is. So when you see actual right there in terms of y, that's what the dot is. And then the line itself is the predicted. So the predicted right there comes from the line. The line makes all these predictions. Anything on the line is a prediction. And then the residual is the distance. Now this would have a positive residual. You could estimate a residual if you saw something like here, if this was 0 and it went up to 40 and this was at 20, sure, then this would be plus 20. That's the residual. It's how much that misses by, because it was predicted to be around 20. We're just tracing over here to where it was kind of predicted from the x. The x might have been 10, so maybe the equation is y hat equals, you could say 5 plus 0.5x. And we're not using names of x and y's, which we usually do. But look, if you plug in the 10 right here into the equation, you would get that, ooh, now this isn't correct. I need to change it. So this needs to be 1.5. There we go. Now, if you plug in 10 right there, you'll get 15, or 1.5 times 10, and you'll get 20 is the predicted y value. And that is the predicted, but this point right here has coordinates. We're doing a little math. This point right here has coordinates of 10, 40, and that's its xy coordinates. So the actual value of it is equal to 40, but the predicted value of it is equal to 20. And you're just plugging in, once again, like we said, you're plugging in 10 right there. You're plugging 10 right there into x. So you have to remember that the formula for residual is actual minus predicted. It's how much the model misses by. Understanding this conceptually and visually is a good thing to understand that if you have a line going down like this and you have a point down here, there's going to be a negative residual, because when a residual is negative, the actual is lower than the predicted. The line's the predicted. Just hold your arm up and make a predicted line. And then if you're above it with the dot, then it's a positive residual. The dot is higher than the predicted. If a dot, my wife's like, why do you say it like that? I say, I'm from New York. If the dot is on the line, it has a residual equal to 0 because there is no miss. Some of the residuals from a least square line will be positive and some will be negative, pretty much usually, unless they're all 0. My Pearson should know there's technicalities to this. Unless they're all 0, this statement is true. Unless they're all 0. No. Some of the residuals are positive, some are negative. They kind of do a balancing act, but they could technically all be 0. It's a technicality, my Pearson. If you're wondering what that would look like, it would simply be a line, and then all the dots would be on the line. That can happen, perfect fit. Rarely ever happens, but so my Pearson's like, you don't usually get that, so maybe we shouldn't even mention that. But that's a technicality. Least squares means the sum of the squares of the residuals are minimized. And yes, the sum that, no, they did it. This one always gets me. This one is a very technical one, and I'm not going to go into too much detail on it. But when we do residuals, some residuals are positive, some are negative. So you get residuals down here, and like the line cuts through the middle of them. It doesn't look as clean as this and as perfect as this, because usually there's tons more dots. But what you do to a residual, this one's negative, you square it and you sum them. So the way they're using sum right there, they said sum right there, but it should be the sum, because you actually take the sum of the actual minus the predicted, and you square it. So the sum of the squared residuals, and this gives you a quantity of sum of squared residuals, SSE, sum of squared error rather. Residuals are errors, and then you see how much error there are. Now, if you're wondering why would you square it, it's because, and this is a good, teaching the test moment. If you add up all the residuals but you don't square them, you will actually get 0. So some residuals are positive, that one's positive, and some are negative. And because of this, they do this balancing act. So if you add up all just the residuals themselves, you get 0. So by squaring them, you make them all positive, and that's why we do a sum of squared residuals. So it should be the sum of the squared residuals, not sum of the residuals. No, it's sum of squared residuals. The big note to take right there is that adding up all the residuals will add up to 0. It's because the line cuts through the middle. Even if the residuals are 0, like in our previous example, then if you add up a bunch of zeros, you get 0. So huge note to take, and often a test question, summing up all the residuals always adds up to 0, and then try to understand it conceptually. That's where you understand it better, that if you had a line right here, that some of the points would be below the line, some would be above, and the line kind of cuts through the middle, such that when you do residuals, some are negative and some are positive, or we could do different color for positive, and the line kind of does the balancing act between them. It's not as clean as this usually, but mathematically, like it is a mathematical fact that if you add up all the residuals, you will get 0, and that's why we square them to make them positive to find a quantity of error. You can't figure out how much error there is unless you square them and then sum them up to find out how much total error there is. A little more theory than we get into 201, but adding up all the residuals always adds up to 0. That's a fact. We write y hat to denote the predicted. Yep, that's true. It's just a fact. We talked about that earlier. So notice a lot of what we're getting into right here is more memorization, that E is the residual and Y is the actual and Y hat is the predicted. You'll oftentimes see me write things like wrap, residual equals actual minus predicted. And that's not notation, that's just a memorization thing. The notation is E for residual equals Y, which is actual minus predicted, which is Y hat. Okay. One question down, a few more to go. Get this whole homework done. Step to a 1, chapter 7, homework. Question 2. Okay, with question 2 and my tag popping on my shirt, a least squares regression was calculated and they give us the line. So the only thing we really need right here is the line to figure this out. Now, what you want to do when you get a line like this is you want to mark everything on it. We're going to grab the line. Nice and big right here. And then we're going to go back and paste it into a new sheet. Who is calling me? Random numbers and random calls. Got a text too. Felt the text and then heard the call. So here we are with the equation. Who is that? It's an oxo number. Someone being like, are you streaming on the internet? I say, yeah. This is the y hat. That is the intercept. That is the b1. And this is the x. Oh my gosh. We gotta... Oh, yeah. I know what that's about. Okay, we gotta give them a call back. It's weird, it's like annotating the message. Should be like, you work. It's fine. So many things. Okay. And so now we have y hat, which is the predicted value. And we need to go in here. A newborn baby that is the value of x. That's how long it is. And weighed this. That's its value of y. If you notice, a lot of this really boils down to notation. It wants us to find, for this problem, the residual e. So it's wondering, what is e? And with e right here, my hair is really flat today. With e right there, we are trying to figure out the residual, as in how much do they miss the prediction by. So the first question kind of loops into this. How much do we miss the prediction by? So let's go ahead and make the prediction. To make predictions in a model, you have to insert the value of x. So that is the value of x right there. And then these two values right here, I'm going to highlight it, but they're not the same. That's not the same. That's y. The model predicts y hat, as in, we're going to make a model right here with this, and here's the intercept down here somewhere, and then the x value they want us to plug in is whatever x this is, and then the slope is going to be this little doohickey right here, and then I think we color-coded almost everything except we need the actual value of y. And I think we'll find out, because I don't know if it's above or below yet. The actual value of y, and I'm going to change that because that kind of looks like the same color of the slope. So let's go here, the nice orange, UT orange kind of. And we're going to put it maybe here. And we're putting it above the x. And the quantity we want to find is this residual quantity. And the residual is going to be that. Now I am guesstimating it's a positive residual. And that would be it's above the line. We do not know that yet. But notice how everything here is color-coded. Even the E is the black dot right there, or the black line. The predict, I shouldn't put a black dot right there. The E is just the distance something is above or below. It might be a positive residual. It might be a negative residual. And now what we need to do is we need to get the prediction to do the actual minus prediction. If you notice how I color-code this right here, when we go to E, which is the black line right there, is equal to the actual, which is Y, minus the predicted, which the predicted is y hat. So we have to figure out the prediction from the line. So we're merely going to take and plug in x into the model. So plugging x into the model gives us 48 right there. We're just literally going up right here and plugging in and finding out what the model predicts at that value of x. And then let's times that by 0.1692. Negative 5.22, and we're going to plug in. So let's find out what we get. Okay, so 48 times 0.1692 minus 5.22. And we do. It is above. So the baby weighs more than it was predicted to weigh. So this distance right here, what is it? Well, this spot right here is about 2.9. This spot right here is about 3.0. And so we could put a little 2.9 right there and 3.0. It's not exactly, but the distance we are looking for is literally going to be this distance right here. And that's what E is. E is how much you miss by. It's just called a residual. And it's that distance. So it's about 0.1. We can get a more exact figure on it. It's basically 0.1. It's, for all intents and purposes, 3 minus that right there, because it's actual, which is 3 minus 2.9. It's positive because the actual is higher than the predicted. I guessed it correctly. And the formula right there is 3 minus 2.9. Make sure to save your values that when you're going through doing this right here, you would get that the actual, we already know the actual y equals 3, and predicted y hat equals 2.9, and carry decimals. And then we're just doing actual minus predicted up there. So really good question, kind of a shorter one, and you just have to know the steps. It should be about 0.1, round to 3 decimals. Ooh. Oh, there we go. Okay. So I wonder if it would have accepted 0.1. Would it have? Nope. Did we do everything correctly, or did we make an error? It says round to 3 decimals. Really? Wow. Man, that one wants some accuracy. That is very, 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 very accurate. So then what does this say? This is basically interpret the residual, and you should be able to do this on your own. We've already drawn it out right here. The baby actually weighs more. Whenever you see y, think of the actual value. So you can see the orange dot is higher than the yellow prediction line. So the baby weighs 0.1 more than it was predicted to weigh. Huge things right there to know. It weighs more than was predicted. Then you should also know because it's positive. Because when a residual is positive, the actual is higher than the predicted. So really good stuff right there, and you should know that. Okay, probably a quick one right here. Let's see right here. 1733, Stat 201, Chapter 7, Homework, Question 3. And try to draw these out. Like, more pictures you can draw, the more you can do it on your own, the better you're doing. If the correlation between two variables is positive, the slope of the linear model will be positive. It's a fact. It's because correlation tells you the direction. Strength, direction, form, unusual features. Well, that was easy. And the slope of the line is the direction of the correlation. So yes, if a correlation is positive, then the line will have a positive slope because correlation tells you strength, direction, form, unusual features, direction being positive or negative. So not too bad, not too bad. Okay, well, that was an easy one. Stat 201, Chapter 7. There's not much else to say on that. Correlation tells direction, and slope is the direction. Disk drives have been getting larger. Figure out the slope, and let's look at the model. Okay, so they give you a bunch of notation right here. They also give you stuff we can drop into jump, and we get the mean of the y, the mean of the x, the standard deviation of the y, standard deviation of x, and the correlation. Very strong correlation right here. We're going to do this inside of jump, so get jump ready down here. Click the little box right here and go to copy to clipboard. Now click Control-C or Command-C, Control-C on a PC, Command-C on a Mac. Now that you've got it copied, go into jump right here. Inside of jump, wait for it to open. Once jump opens, go to File, New, Data Table. File, New, Data Table. Under File, New, Data Table, you want to then go to Edit, and we'll have one of two chances right here. Now, if you notice, it does look like it has column names over here. Column names are these things above the columns, hence names, column names. So don't click inside of here yet. Go to Edit, Paste with column names. And why are we doing that? It looks like it has column names to me, and we have it. If it pasted like this, you've done it incorrectly. Notice how the column names here are in the first row. That's bad. You don't want this. If there's no column names, you paste normally, but if there's column names, paste with column names. Make sure both of these are blue. If they're not blue, restart and try pasting with column names in a new sheet by doing Control-N and then Control-Shift-V, it's the quick keys, or use the edit paste above. But as long as both of these are blue, you're good to go. Okay, now that we have one sheet, we only need one with blue. We're going to go in here and go to Analyze Fit Y by X. Under Analyze Fit Y by X, there you go right there, Analyze Fit Y by X. I did videos a long time ago, and people were like, you got to pause. Don't go too quick. There we go. We are going to predict either price or capacity. So you have to think, if you're buying a hard drive, what would you care more about? Well, you kind of care about both. But which one would you want to predict? And my guess is that you would want to predict the price. So you say, why is it a certain price? Maybe the capacity explains that. So capacity explains why hard drives are a certain price. Just kind of do a circle right here. Capacity explains why things are a certain price. Click OK. Now you can see right here there is a bit of non-linearity to this model. You can see it bends. I'm going to show you one cool thing real quick. don't do this. You can if you want, but you can fit higher order polynomials like a quadratic model, and the R-squared is basically 100%, meaning the quadratic model explains about 100% of the variation. I'm going to remove this fit, but you can always try these buttons over here and see what happens. Polynomial fits bendy models, so you could fit this very high order polynomial model and get an R-squared of basically 100%, but that's overfit. Hard drives past 30 just completely drop off. That's called overfitting. That's a topic for another day. We're just going to fit the line, which might not be the best fit for the model, and I'll show you again where I went. Go to the red arrow and go to fit line. You don't need to add in those extra fits. It's just kind of cool extra things we can do in stats. So you can see the equation of the line below it right there. There's the equation of the line. And once again, do know the equation. I'm going to delete down some decimals. How many did they want? I'm going to delete down to 2 decimals. Here, that'll go to 20. I didn't check. Don't do what I'm doing yet. We'll say capacity. Now, the reason I'm doing this right here is to show you a few things, because you should know how to look at this output. Let's go ahead and take this output right here and make sure you can read and understand this output. So very important kind of lecture part of the video right here. And you have the equation. So here it is. Right here, you have the intercept, which is B0. That is the estimate of the intercept down there. Notice how it goes into estimate of intercept. Right here, you have the slope coefficient. The slope coefficient is right here, the estimate of the slope. Down here also, you have the name of the x variable, and that's the name of the x variable there. And this is going to be the predicted y, so that is the y hat. And we'll add in the other ones right here. This is the name of the x variable. And last but not least, we also have the B1. So you should know down there that that is B1, and this is B sub 0. And then also over here, we have the significance of the model, and it is statistically significant, which is the significance of the slope. Because if the slope has a significant non-zero value, that matters. If the intercept, which is this one right here, has a non-zero value, as The Rock would say,
it doesn't matter.
No one really cares about the intercept. Hey, what's up, Evan? I'm struggling with the Kaggle. We went through it in class, but I'm sure what it's supposed to be producing. Is there any chance? Yeah. Are you free to come by office hours today? Because I don't want to give too much. Like once you, like if you, or send me your work. Send me your work. I don't want to put too much out there. Thank you, Evan. Send me your work, or if you can come by office hours, I might do that one that way. We're doing it right now, talking about regression right here, but you're basically making a predicted vector. Download the submission file and look at what the submission file looks like. And if you have your file from class, it's basically the same steps. But send me what you have, or swing by office hours. But how's that sound, Evan, right there? And I guess one last value right here we should know. Let me know what you're thinking. One last value. What color should I use? Let's go with purple. This value. R squared. So this is kind of where we're at in 320 right now. And then we just build off this a lot more. So with this right here, you should know how to interpret all these values. So if you take a look at the chat's going to have Mubot talking about slope, intercept, and R squared. So Mubot's about to put the interpretations for slope, intercept, and R squared in the chat. And let's take a look. Mubot, talk to us. Oh, he's not even awake? He's awake. What? What in the world? Windows security. What's going on, Mubot? What in the world? Well, we're gonna worry about that later. He's something weird going on. Mubot might be in trouble. It's like I have no idea what's going on with that. First time I've clicked it and it said crazy things. Windows thing might have, who knows, but well, We're gonna figure out what's going on with that. That's another thing on the list. Aha! Okay. Mubot, no! Might re-download Streamlabs. We'll find out. I might literally re-download that program, and that might fix it. Hopefully. I'll probably do that, and it might destroy Mubot, or we'll find out. Anyways, let's go write the equation. We have the equation of the line, and with the equation of the line, we go back into here, and it asks for the intercept. So once again, we've marked the notation right here. We know the intercept is negative 299.20, and it does want to round to that. There it is right there. Check the answer. What? Did I round incorrectly? Negative 299. Oh, the slope. Haha. The slope is 142.25. 142.25. Is that right? Let me double check. So Mubot Windows security. I know something's going on weird, and there it is right there. Like I'll try resetting the computer or something. What does the slope mean? For each additional terabyte, we expect the price of the hard drive to increase by B1 units. For each additional X, we expect Y to increase by B1. It indicates for each additional terabyte, we expect the price to increase by a certain amount. I am just out of it today. The slope indicates for each additional gigabyte. Is it gigabytes? Wait. It indicates the additional, the additional price per terabyte. Yeah, for each additional. So the way they're wording it, let me slow down a little bit here. I know I've got my Monster Energy drink right here. What you want to be able to do, we'll slow it down a little bit, because on the test, you have 3 written responses. And the 3 written responses are, the slope is going to be for each additional X, we expect Y to increase by B1 on average. The intercept is going to be when X is equal to 0, we expect Y to increase, we expect Y to be B sub 0. Oh my gosh, there we go. Okay, and the R squared is going to be blank percent of the variation in Y is explained by the variation in X. So also for 320, you should know these. So you have to plug in your values right here. So plugging in the values, let's make this a little bit bigger. Let's plug in the values. I really do hope, I know sometimes people skip these parts of the video, but these are maybe the most important parts because they are literally what's on the test. And I would prefer just to write out my answers or say them as I was trying to do rather than read their answers. So R squared, you're going to plug in the value of R squared right here, and then you're going to plug in Y and X. Here, let's highlight where Y and X are, so we don't need R squared anymore. Kind of, sort of. You have to know this output. I did put a little bit of jump output on the 320 test, so you have to know how to look at output and understand what it is, because I don't know what output you'll be looking at in the future. Because you could look at jump, Minitab, SAS, SPSS, Excel output. There's tons of different outputs you could be looking at in the future. And I don't know what outputs you might have to see and might have to explain, but all the output kind of looks similar. So if you take a look at this right here, for each additional terabyte of capacity, we expect price to increase, and that should be increase slash decrease because it could be negative, by, I'll put, is this logical? Is this logical? Okay. We expect price to increase by $142.25. Scary, scary. When capacity is equal to 0, we expect the price to be negative $299.20. That's not logical because you can't have a 0 capacity hard drive, nor would a hard drive cost negative dollars. So both those things are illogical right there. You can't have 0 capacity, and hard drive can't be negative. And then 97.5% of the variation in price is explained by the variation in capacity. 97.5% of the variation in price is explained by the variation in capacity. Once again, just plug in where I have it color coded and write these down. Please write them down and try doing it. Try saying them out loud. The more you say it out loud, the more you can write them down, the better you can do. For each additional terabyte of capacity, we expect price to increase by $142.25. When capacity is equal to 0, we expect price to be negative $299.20. This is illogical because you can't have a negative capacity, nor can you can't have negative price, nor can you have 0 capacity hard drives. And then 97.5% of the variation, make sure it times by 100. 97.5% of the variation in price is explained by the variation in capacity. Does that make sense, Evan, right there? These are 3 values, and for R, the output looks a little bit different, but it kind of looks like this one down here. And this is a statistically significant model because the slope is statistically significant. So make sure to know how to do that. We have the intercept down here. I think I've memorized it. I've seen it a lot right there. That is the intercept. And what does this mean? It would be a 0 terabyte hard drive. It indicates the price of a hard drive with no capacity is meaningless and should not be interpreted. Write out the equation. So now it just wants us to put the intercept plus slope times capacity. And remember, this is all found in your jump output right here where you have the equation. So there's the equation right there, the B0 plus B1X. And great job, Evan. So make sure to plug in those values and you'll get them. And then what would you expect the price of a 20 terabyte hard drive to be? Well, we go right here, and all we need to do is plug in 20. So this is what the predict function is doing inside of R. It's just plugging in values when you make a value to make predictions with, or give it new values. You just plug in the predict function, and we can now predict for a 20 terabyte hard drive. We type 20 times that by 142.25, and then we subtract from it 299.20, and there's the prediction. Wow, yeah, things don't cost that much anymore. Round to the nearest cent. I think that's right. Yep, just didn't have any extra decimals. You find that it costs this, so it costs less than it was predicted. So that's going to be a positive residual. Once again, this is the actual, and you should be able to once again a lot, do the notation on these. So what you want to think about here is when you have this is the predicted value from an X, and this is the actual value. So you can do residual equals actual minus predicted. And right now it is it actually costs, wait, you found that it costs this. Oh no, that's not a good buy because it costs more than it was predicted to cost. So no, because the price is more than the predicted price. How much more or less would you pay compared to what the model predicts? So now they're just asking for the residual. So now they're literally asking you to go here and take 2560 and subtract from it, and you're paying 14.2 more. And that's literally just a residual. Does the model over or underestimate? That's usually where people get it wrong. So the dot's up here and the model's down here. So we always get the actual price. Kind of. Kenai, good to see you there. It just depends on what the question asks. And notation is so key. Notice how I'm marking all these right here. And what we see right here with a positive residual is the model over or underestimating. When the residual is positive, is the model over or underestimating the price? When the residual is positive, is the model, this is a positive residual right here, like that dot is above the line. Is the model over or underestimating? A lot of people get this last one wrong and they have to redo the whole question. So the model is the line. That's what the model is. That's the equation of the line. It's it's under the dot. So when you underestimate the price, there's a positive residual. As the price, great job, Kenai. Because this is the actual and this is the predicted, and then the residual is positive, because if you do, like, you can just make up fake things right here, like 100 minus 80 equals positive 20. Like, those aren't the actual numbers, but if you predicted 80 and it's actually 100, then there's a positive residual and the model underestimated it. So the model underestimates the price. And that's what happens when you get a positive residual. The correlation is very high. Does the model make accurate predictions? It's really due to the nonlinearity. It's not because there's few dots. Those are just nonsense. The model is accurate because it has a very high correlation. No. The model might not be accurate because there's an extreme outlier. Yeah, kind of. I don't love that one. Truthfully, the right answer to that is the model. The line does not have a really good fit. Do you see how the line has this weird fit right here? And it's due to the model truly has a nonlinear relationship. This fits a lot better if you look at the misses, and you can see the residuals, like there's a negative residual here, but to the polynomial model, it's very close. So you can actually do residuals from nonlinear models, and you can see the residuals got smaller because like that one's perfectly predicted now. That one has a positive residual, zero residual, positive, barely, negative, negative. And do you see, keen eye, how I'm saying that? Like when I'm like, oh, these dots right here, if they have positive or negative residuals, I can look at it and say like positive, 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 negative, negative, positive, zero, basically, positive, and just looking at them visually if they are above or below the model. This is a nonlinear model. We're not doing nonlinear models, but you can always try to do them if you want. And if you look at the linear model, you can see like the line doesn't go through the start of the data. So this is a bad fit model. The line doesn't really fit the data because, I mean, it doesn't look linear, especially at the start. You have to go out to where the outlier, yeah, so they're kind of right. I mean, it's extreme value. It's not really an outlier because the model fits the point. Do we have a lack of fit? Nope, I know why. So right here, we have residuals. This one's a bit easier. That was a big kind of lecture part of the video right there. So thank you everyone for listening into that. We basically did a whole bunch of lecture. I hope when I re-download MuBot, he keeps his mind. I have no idea why. I'm gonna have to like Google like to see like what's going on with it. Question 5. Over on the right are residuals, and which of these contributes most to the sums of squares? This goes back to one of the first questions we did with sums of squared error, where sums of squared error is literally summing the squares. It's not residual because it's not on the line. So something has a residual by how much it misses by. So a residual is literally the distance something is above or below. So every single dot will have a residual. Does that make sense? But if a dot is on the line, it'll have a residual of 0. So anything above the line has a positive residual because the actual, which is the dot, is above the prediction line. Anything on the line has a residual of 0. Anything below the line has a negative residual because the actual is lower than the predicted. So via the formula actual minus predicted, we can figure out the residual for any single dot. So every single point has a residual. It just could have a residual of 0, which means the model didn't miss it. Like these have very small residuals, and this has the biggest residual. So when it says which of these hard drives contributes most to the sum of squared error, well, the error right here is the residual, and it says sums of squares residuals, which is error. So which of these would have the biggest squared residual? Now, remember I talked about this earlier in question number 2 or 1, because the reason we square residuals is to make them all positive. So think about this. You're just looking at the absolute value of a residual because the one with the biggest square is going to be the one with the biggest residual. I tried my best to draw squares. So which size hard drive has the biggest squared residual? Which size hard drive has the biggest squared residual? Is it 4, 3, 1, 0.31, 0.27? Which of them has the biggest squared residual? Not 4, because, well, good answers. Good try. MuBot's not awake right now. I can't give out points. The computer thinks he's a virus. That's great. MuBot will be back here next time. So with this right here, all we do is look at the size of the residual, and it'll be 1. Because you just look at the absolute value of the residual. Because when you talk about squared residual, you would literally just add in a new column right here. And the squared residual is how we can look at all of them. Because if you add up all the residuals, you get 0. And if you go to squared residual squared, this would be like 11, this would be like 10, this would be like 24, this would be like 340. Exactly, because when you square, so the biggest squared residual, and I'm making these up, I'm kind of guessing at the numbers. This would be like 470, and this would be 450, and this would be 226. Does that make sense? So the biggest squared residual, as the rock would say for the sign doesn't matter because when you square residuals, they all become positive. So you don't even really worry about the sign. It literally is just asking like which of these is the biggest residual. So a negative residual means what? That the hard drive costs less than it was predicted because it has to be below. So it would cost less than it was predicted to be. And its capacity, so like when we guess via its capacity or make a prediction, a residual of negative 21.68 indicates that the drive costs $21.68 less, because that's a negative residual. Yep. So make sure you know what it means for a residual to be positive or a residual to be negative. And you can see right here, we were doing this with the hard drive model right here. And actually we had it visually over here on the hard drive model. So this hard drive will add back in the line, remove fit, and add back in the line. This hard drive right here costs less than it was predicted to cost. Why does it cost less than it was predicted? Because it has a price of $1,079.55, but it was predicted, and we could kind of look at it's predicted a little bit by just putting the model up to the top. It was predicted, oh, let's make it so, here we go, and we'll do it in units of 50. There we go, and hit OK. There we go. It was predicted, oh, it's, wait, that's just price. Its price is $10.79, and it's predicted, oh, it's right about, maybe it's very close. Oh, I need to do this. Let me go over here, because I think, yes, there we go. Because there's its predicted. There we go. Looks like something is off. Okay. It was predicted to be about 1400. We'll put it right here where it says 14 or 1450. Wow. So you can see this is the residual. Does that make sense what a residual is? It's that much below. So the hard drive itself costs less than it was predicted to cost. And you can see if you go up here at 12, you would hit the line here. Then you'd go over to where the prediction is over here. We'll just call that 1400. And then it maybe was 1100. I know it's not exactly that. So that's a distance of $300. So this hard drive right here has a negative 300. Just via estimates, we're just estimating it costs $300 less than it was predicted to cost. And that's what they're getting into with these questions. R squared, they show you an R squared right here at the bottom. So I don't want you to use their interpretations. Are we doing hard drive still? This is people working and the sales. And the R squared is 97.8. So it's people working in sales. So I want you, so X is people working. Try to write it out. I'll give you a moment right here. And Y is sales. So try writing this out right here. I'll highlight for you. So there is sales, which you're trying to predict. And then there is people working. Don't read their answers. Don't read their answers. Because on the test, you have to write this out. So if you get in the theme of just kind of clicking what I click or being like, I don't need to write it out, then you have a hard time on the test. So how would this go if you write it out? And I've basically got it for you. You just have to put in the numbers and the words. But how would this go if you write it out? What would it be? What would this be? Any thoughts? So if you're at home right now watching this, try writing it out rather than looking at the answer I'm about to put in. Shouldn't be that hard, and it's really good practice because when you get to the test, you got to write it out, and then people say, I have no idea what to write. And I say, no, we do it all the time. We do it like 3 different days in class. You want us to use the R squared? You right here, just plug in. I'm going to highlight in yellow right here. You're going to put in the things right here. Those are the only things we have all the information for on this problem. Just inserting what is the R squared right there. So 97.8% of the variation in sales is explained by the variation in people working. Boom, I wish I could give you points right now. Great job, Evan. That's exactly it. And then we go back here and we look and we say the value of R squared is, which is the percent of variance. They're calling it variance. Variance and variation are basically the same thing. In the sales that can be accounted for by the regression model on, it should be by the regression model of number of salespeople working on sales. No, it's on X, Y on X, I think it is. By the regression model of sales on number of salespeople working. So the percent of variation in sales, because we want to understand sales, So R squared was 97.8%. Of the variation in sales can be accounted for by the regression model on sales y on x. Check answer. Really? It's x on y? Or I got the R squared wrong. I hate that they do that. What am I doing? Wait. What did I do wrong? Let's see. 97.8% of the variation in... No. Okay, wait. 97.8% of the variation in number of sales workers? No. People working? No. The R squared is 97.8%, which is the percent of variation in sales that can be accounted for. I feel like I've selected the wrong number. What did I do wrong? What did I do wrong? I wish I could give you points. I see it now. What did I do wrong? See if you can get it. It's on this screen. We're doing R squared. So what did I do wrong? It's not squared. Great job, Evan. There we go. And so R squared is R squared. It's not the same thing as correlation. It is R squared, not squared exactly. No! So it should be the first one. Yeah, it was the first. I was like, the thing is once I saw those, I knew 100% that it's not. Let me just show you the other ones again. I know 100% that we're explaining why. Like I always, the y on x, I usually get a little bit tripped up on. I was like, did that trip me up this time? I've had that one get wrong. But we're trying to explain the percent of variation in sales, so it can only be C or D. We're not trying to understand the variation in salespeople working. That's the X variable. The X variable does the explaining. So 97.8 or whatever, 95% of the variation in sales can be explained by the variation in the X variable. And they just literally say the regression model Y on X. So now this one would be regression model on Y on X. So something like 95.6 usually goes out to that. And that's not it. Here, we'll try another one, 95.4. Nope. Once to one decimal. Let's try 95.8. We're just guessing. Nope. It was 87.6. So we can figure out what R is. As long as R is positive, we can go right here and go 87.6 and square root it. And there's R, 93.59. Don't go to the next question. And there's the 93.59. Once again, you can get R squared and turn it into R, but I would also need to check the direction and see that this is positive, which the numbers are going up together, which is positive. So we'll do one more shot at it. You ready? Let's go one more try at it. 98.5, which is the one we had before. Blank percent of the variation in sales is accounted for by sales on the other one. That's going to be like 95.4. Nope. 95.6. Oh, I actually have to do it. 98.5. 97%. There we go. So almost on the dot. Final check. Got it. Just square R. And last but not least, if our data in a scatter plot is straight enough, we can model it with a what? Don't click their answer. Oh, I didn't put that last one in here as a timestamp. What is the answer to this? If our data is straight enough, we can model it with a what? Which is this whole chapter. And great job, Evan. Thank you for being here. If our data is straight enough, we can model it with a what? And Evan, I'm going to do a little bit of 320. Thank you for hanging out. We've got the full homework done. So you know what? We got time. So let's do it, right? Yeah, I'll show that again. Noel, you got it. And so if our data is straight enough, we can model it with a what? Don't click their answers. Think, why do we check the straight enough condition? Don't click their answers. The more you can do these without clicking answers, the more you understand it. So if the model is straight enough, then we can model it with a what? Don't click their answers. What's the whole point of doing straight enough? You have to be like, well, we're checking straight enough to see if we can do what? That's the answer right there. The whole point of QQ is two quantitative variables. Well, so wait, we're going to model our data with a what? What kind of model or kind of prediction thing are we going to add to it? We're going to add a what? We can add a what to the data. QQ means we need two quantitative variables to do regression. No outliers means we want no outliers. What does straight enough mean? That the what is a good idea. Not outliers. Good guesses. Take one more guess. You got this. I wish I could throw some U-Ball points. So what's the whole point of straight enough? The idea of fitting a what to the data. The whole point of straight enough is that we're trying to fit a what. So QQ is to say, do we have two quantitative variables to make a scatter plot? If we do, we can continue. Straight enough says, is it a good idea to add a what to the data? No outliers says we should not have outliers. Outliers are bad because they can pull the data in any direction. And then plot doesn't thicken means the model should have about the same consistent strength the way through the model. So QQ straight enough, no outliers, plot doesn't thicken. But what does straight enough mean? What does straight enough mean? It is a good idea to add a what to our data. Is it a good idea to add a what to our data? A line. A linear model. Add a line. Because that's what we're doing in regression, writing a line. So is it a good idea to add a line? There we go. Does that make sense? Straight enough means the line's a good idea. For the last one right here, with the r squared, we are simply going and taking r. Great job, Noel. We're taking r right here and squaring it. So that is the r and square it. So there's r, which is correlation. Squaring it makes it no longer correlation, is now r squared, 90.6. And then we say 90.6% of the variation in sales can be accounted for by a regression model y on x. Make sure to square your r, which I didn't do the first time. And there we go. Does that make sense, Noel, for this one? It's blank percent of the variation y is explained by the variation in x. And r squared is the value, or you take the r and you square it. Take your r and square the r. Evan, are you still here? Ah, no, I just undid the change. You gotta be kidding me. Can I undo the undo? Oh, no. Well, I'm gonna have to put timestamps in here later. Oh my God, I literally clicked a button. Undo changes. Undo the undo. Stat 201, chapter 7. Homework. Question 1. Okay. Mubot's broken. I just deleted the timestamps. Bank's calling. Ah! Oh my gosh. The week starts and everything's on fire. This is the way it goes. Oh, okay. Loading up R right here real quick. Okay, loading up R. Here we go. So, just briefly, you want to load up reg class here. We'll put this sad music. I know we need the sad music and everything's on fire. It seems like everything's on fire. Everything's on fire. It's craziness. Here, we'll try to hit the sad music. It might be sad music. I don't know. Everything's on fire. Let's do 53. I've got the everything's fine, right? Watch this. It took like a week to make. Okay, here we go. That's what we played before the project. Got reg class loaded up. Thank you so much. That took a while. It's one of those I'm very proud of. I made that one. Like I had the camera pan and like that was a lot of work. Probably someone could make that in like an hour if they like could film it all. The fire effect took a while. Like I had to like map the fire, like like trace the fire to my arm. So it wasn't real fire. Let's make a model. LM weight tilde miles per gallon. We'll do miles per gallon from weight. Miles per gallon tilde weight, comma data equals empty cars. There we go. This is the same sort of summary you see in 201, where you see the estimate of the intercept, the negative slope, and the significance of the slope down there, and then the r squared, 75.28% of the variation in miles per gallon is explained with the variation in weight. We can also visualize the model really quickly right here with the following, and you can see the negative relationship. And it looks pretty linear. We can also do a check on this, not that. Check regression, and we can see if the model is a good fit. And linearity has a bit of a problem. That's how we check the linearity. Normality of residuals looks good. Everything else is fine. P-values are fine. So what you want to do for 320 is you want to make predictions, but you want to make predictions on new data. So this is where people might be getting stuck, is you have to read in your new vectors. If you're stuck on any of this, you need to talk to me as soon as possible. Also, the lab last week basically did it. So your file from last week's lab is going to be a huge help. But if you're stuck, you need to be like, hey, Brian, I am stuck and I need help, because you need to know how to bring in your new data such that you have a data frame of vectors that you can predict from. Notice how the model is using weight to make predictions. So I can just add in random weights right here, and then I can go here and say new equals data frame. I can get predictions for the new data frame. I can also write this to weights right here, save it here, and go to write.csv, or we need to put this into a data frame now. So data frame $weights. Ooh, where's my weights? There we go. Null. Oh yeah, because nothing's there. Yep. There, sure. Oh, it's going. Oh no, it did do it. Let's see. Look at the data frame. Oh, and this is not perfect right now because we're gonna have to do some copy pasting. But there's 49 observations to predict, and you need to bring in the new days. And I don't want to do the whole thing for you, but you want to. You could literally just start copy pasting these into your file if you have predictions. It's gonna take longer than it would if you write it. If you go here to write data frame, comma, prediction file.csv. And now you have this file right here as a CSV. I'm going to go to my computer, and you can just search your computer for it. There's prediction file. Make sure it opens just as. But here's the problem you're going to run into, and this is a good thing. You'll see that here in one moment. And we can kind of end with this. So if this is your prediction file, you won't be able to upload this because it doesn't have the right structure. Remember in class, we talked about your file has to look exactly right. If it doesn't look exactly right, then you can't upload it. So it needs to have the exact structure as the submission 0 file. So check out that submission 0 file, make sure it has the exact structure. And with that, we did all of chapter 7. We talked a little bit of 320, computers on fire. Till next time, bye for now, everyone. Bye, bye to all. I gotta make some calls. I gotta get random calls. Ah!